Hello friends, this video is on exponential functions. Exponential functions are functions that have the variable as the exponent. So if we look at our very first example here, we notice right away that our value of x is in the exponential area, is the power. That makes this an exponential function. The base of the exponential function is 2, and the constant of the exponential function in this particular problem is 5. Let's say that we are going to allow x to equal 0. So right here, x is going to equal 0. If we are going to allow x to equal 0, then the function is, using x as 0, we have 5, 2 to the 0 power. Now, any number raised to the 0 power is the number 1. And therefore, when x is 0, the value of y is 5. So this is the number 5, which, if we look at what we have in our notes here, we will notice that right here, it tells us that this value, this constant, is the y-intercept when x equals 0. All right, so there we have it. And now we know why. So let's change the value of x. Let's change the value of x. Let's say the value of x now, instead of being 0, let's say the value of x is going to be 1. If the value of x is going to be 1, we'll put a 1 in the function, and 2 to the first power is 2, and 5 times 2 is 10. So when x is 1, y is 10. Let's try it again, but this time, let's try it with the value of x being 2. So now we're replacing x with 2. 2 to the second power is 4, and 4 times 5 is 20. Let's do it again, but this time let's raise the power to 3. So when we raise the power to 3, we replace x with 3. 2 times 2 is 4, times 2 is 8. Now our number is 40. So when the value of x is 3, the value of y is 40. Let's try it again. Let's try it again, but this time, let's let the power be 4. So let x equal 4. So the power is 4. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. And 5 times 16 is, you guessed it, 80. Do we see a pattern? I hope we see a pattern. I think the pattern we see is to go from this line to this line. We had to multiply by 2, and then 10 times 2 is 20, and 20 times 2 is 40, and 40 times 2 is 80. So we're multiplying each time by 2. Well, that's all well and good. Is it true when our powers are negative? Let's go and let's look. So let's practice when x is equal to negative 1. So we're going to substitute negative 1 in for x. Now, 2 to the negative first power, we learned in Algebra 1 that that means 1 over 2. So that would be the number 1/2. And 5 times 1/2 is 5/2. So we can put in the number 5/2. If you don't like 5/2, you could change it to 2.5. All right, let's try again, but this time, let's change the power to negative 2. So the value of x is negative 2. So we're going to replace the exponent with negative 2. That would make our fraction 1/4, And 5 times 1/4 is 5/4. So we could say 5/4, or if you don't like 5/4, you could say 1.25. Those are equivalent values. Okay, well, what if the exponent is -2? What if the exponent is -3? Well, if the exponent is -3, in other words, if we substitute -3 for x, then we would get this to be 1/8, which means this is 5/8. So this is 5/8. If you don't like 5/8 as a fraction, that's fine. 5/8 as a fraction, as a decimal, is 625. And then we could do it one more time using the number -4. So if we change the value of x to -4, that's going to make this a 16th, which is going to make this 5/16, which is going to make this 5/16, which would be 0.5/16, what would that be, 7? Nope, 25. You'll notice that if you take this number and multiply it by 2, you get 0.625, and if you multiply that by 2, you get 1.25, and if you multiply that by 2, you get 2.5, and if you multiply that by 2, you get 5. So basically, this is the number that all the x's are being multiplied by. And then if we plot those points, let's do that. So the easiest point to plot, I think, would be the point 0.5. 1, 2, 3, 4, 5. So our first pair would go here. That's 0.5. Then 110 would go here. 220 would be at the top of the page. 340 would be off the page. And 480 would be way off the page. So how about if we do -1, 2.5? -1, 2.5 would be approximately here. -2, 1 1/4 would be approximately here. -3.625 would be approximately here. -4.3 would be approximately here. And no matter how we keep going, our fractions are going to continue to be smaller and smaller. So we had 5/16 as our last fraction. In front of that, we would have 5/32 and 5/64 and 5/128 and 5/256, etc. But we will never, ever, ever get to 0. So we will never get to 0. So we do have a horizontal asymptote. The horizontal asymptote is the line y equals 0, or another way of saying that would be the x-axis. And so our graph is never going to touch the line y equals 0. Our graph is never going to touch the x-axis. So our graph is going to move, I'd have a very hard time graphing these, but our graph is going to move, gosh darn it, let me try again. Our graph is going to move very much like this. And that is how our graph is going to move. So let's talk about this real quickly. Let me get rid of some of the stuff just because I need to write down here. Bigger eraser. Okay, so let's talk about the characteristics of this graph. Let's talk about the domain. The domain, we could have picked any number for x we want. So the domain is -infinity to infinity. However, the range can never, ever, 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 ever touch the x-axis. So the range has to be from 0 to infinity. The y-intercept, we know, the y-intercept was 0.5. By the way, we know that from our rules right here that we have highlighted in yellow. Our x-intercept, there isn't one. because the horizontal axis is the x-asymptote. So that does not exist. And by the way, it does increase. Once you get on this graph, it continues to rise as it moves to the right. So it is going to increase from negative infinity to infinity. But let's talk about the end behaviors. The end behaviors are different than the end behaviors we have for polynomials. Our end behaviors, the limit of the function as it moves to the left. In other words, this graph, as it moves to the left, as it goes to the left-hand side, is getting closer and closer to the axis, but never touching the axis. It's approaching 0. It's approaching that yellow line. But the right-hand side of the graph is continuing to move up and to the right. So as it moves up, it continues to move to the right. So as it increases, it also moves to the right. So the right-hand side of the graph is going towards infinity, and the left-hand side of the graph is approaching 0. All right, so let's try the next one. Okay, so we should have, since we have this number is 4, we should have this number should be 4. But let's plug it in and make sure we are correct. So the function is f, we're going to use 0, equals 4, 3 to the 0 power. That is, using 0, 3 to the 0 power is the number 1, and 4 times the number 1 is the number 4. So winner, winner, chicken dinner, that is correct. That is what we expected. Okay, so let's try it with x being 1 instead of being 0. So let's change the value of x. The value of x is going to be 1. 3 to the first power is 3, and 4 times 3 is 12. Fabulous. Let's do it again, but let's do it this time with x equaling 2. So we're going to replace all the x's with 2. That means 3 is going to be squared, which is 9, and 9 times 4 is 36. Excellent. I don't know if you've started to see a pattern here. Let's put in another number and see if the pattern holds. Let's let x be 3. If we let x be 3, 3 times 3 is 9 times 3 is 27, and 27 times 4 is 108. 108. Let's try one more. Let's let the power be 4. So let's let x equal 4. Put 4 in each of these places. So that would be 3 to the 4th power. 3 to the 4th power is 81. Sorry, I forgot what I was doing there. 3 to the 4th power is 81, and 81 times 4 is 300. I lost my place. 81 times 4 is 324. Is that right? 81 times 4. Yep, 324. So this is 324. Okay. So it looks like those are all being tripled. Would that be fair to say? Would it be fair to say that if you take 4 and you multiply it by 3, you get 12? And so we took 4 and we multiplied it by 3 and we got 12. And we take 12 and we multiply it by 3 and we get 36. And 36 times 3 is 108. And 108 times 3 is 324. So what happens if the exponents are negative? Well, let's try it with a negative exponent. So let's change the exponent to negative 1. If we change the exponent to negative 1, this would be 1/3, which would give us 4/3. What if you change the exponent to negative 2? Well, if we change the exponent to negative 2, that means all the x's are negative 2. That leaves us a power of 1/9, because 3 times 3 is 9, so that leaves us 4/9. So this is 4/9. So let's try it again, but let's try it with a 3rd power this time instead of a negative second power, let's try it with a negative third power. If it's a negative third power, 3 times 3 is 9, times 3 is 27. That would be a 27th. That would be 4 to the 27th. And then the next one would be 4 to the 81st. And I will tell you this, if you take 4 to the 81st and you multiply it by 3, you get 4 to the 27th. And if you multiply that by 3, you get 4 to the 9th. And if you multiply that by 3, you get 4 to the 3rd. And if you multiply that times 3, you get 4. So that works. Again, the horizontal asymptote, while those fractions are going to get smaller and smaller and smaller and smaller, they're never going to touch 0. They're going to be incredibly small fractions, but they will be fractions. So because they will be fractions, the horizontal asymptote is the horizontal axis, which is y equals 0. So this is the line y equals 0. Then we plot our points. 0, 4, 1, 2, 3, 4 goes here. I don't know how I accidentally hit the blue color. Let's go with black. And then 112 won't even fit on this graph anymore. 112 was going to be like up here somewhere. So let's go to negative 1. Negative 1 and 4/3. Negative 1 and 4/3 will be about right here. Negative 2 and 4/9 would be about right here. Negative 3 and 4/27 would be about right here. So again, this graph is going to be very, 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 very close to the x-axis, but it's never going to touch the x-axis. So it's going to go like this. It's not a very good graph. See if I can hit those dots a little better. I don't like the fact that that laid right on top of there. There, and then it's going to hit that point, hit that. Just don't like that at all. Let's make that a little bigger. Maybe I can hit it if I can see it a little better. There, I hit that point. It's going to go like that forever. And again, if we go and we make our list is going to be the same as it was a minute ago, only the y-intercept will be 0, 4. So this list will basically be the exact same list as it was a moment ago, only the intercept, make it a little smaller, only the intercept, instead of being 0, 5 this time, the intercept this time will be 0, 4, but none of that changed. Okay, so let's look over here at this one. All right. So if we put 0 in for x, we have 3 to the half power, times 1/2 to the 0 power. That is 3 times 1. That is 3. So when x is 0, y is 3. Okay. What about when it is 1? Let's put it in and see. What about when x is 1? This is 1/2. This is 3/2. Okay. What about if the power is squared? What about it if the power is 2? If the power is 2, that means this is 1/4, which makes this fraction 3/4. Okay. What if it's not a power of 2? What if it's a power of 3? If it's a power of 3, that makes this an 8th, which makes this 3/8. And then this one would be 3/16. But what about if the power is negative 1? If the power is negative 1, we're going to remember that 1/2 raised to the negative first power is the same thing as 1 over 1/2, which is the same thing as 2. Or the easier way to do that is to just take this fraction, flip it upside down, and make the power positive. Either way, you get 2, and 3 times 2 is 6. So what about if the power isn't -1? What if the power is -2? If the power is -2, that makes this fraction this number 4, which makes this number 12. What if the power isn't -2? What if the power is -3? If the power is -3, that makes this 2 to the 3rd, which makes this 8, which makes this 24. And then this would be 48. So, -4 or 48 is going to be hard to graph. The first one that's graphable really is -1, 6. 1, 2, 3, 4, 5, 6. There's -1, 6. Because -2, 12 would be right up here. And then we got 0, 3. 1, 2, 3. And then we have 1 and 1 1/2. And we have 2 and 3/4. And we have 3 and 3/8, etc., 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 etc. But still, what's consistent before is it's still never going to hit the x-axis. It is still never going to hit the x-axis. And it's going to be this curve. Like this. Okay. Now, if you will, please notice this number and this number are exactly the same as here. But we have these translations. So what are the translations going to do? The translation is going to reflect across the x-axis. It is going to move 5 right. It is going to move 4 up. So, if we take all these points on this graph, flip them upside down, move them to the right, and move them up, we're going to end up with this other graph. Okay? So, if we, for instance, take the point 0, 3, so let's take 0, 3. There's 0, 3. Let's move it 5 spaces to the right. 1, thought I hit the green. 1, 2, 3, 4, 5 spaces to the right. That puts it here. Let's move it 4 spaces up. 1, 2, 3, 4 spaces up. That puts it here. And let's reflect it across the x-axis. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. So it would be right there. That would be that point. Okay? Let's try it again with another point. Fair enough. Another point we had was the point -1, 6. So if we start with -1, 6, 4, 5, 6, there's 4, 5, 6. Let's take it and let's move it 5 spaces to the right. 1, 2, 3, 4, 5 spaces to the right. Let's take it 4 spaces up. 1, 2, 3, 4 spaces up. And now let's reflect it. When it reflects, it's going to reflect to right here. Okay, that's excellent. Let's pick another point. Let's pick the point 1 and 1 1/2. So the point 1, 1 1/2, 1, 1 1/2 is right here. Let's move it 5 spaces to the right. 1, 2, 3, 4, 5. That puts it right there. Let's move it 4 spaces up. 1, 2, 3, 4 spaces up. That puts it about right there. And then let's reflect it. So it is 1, 2, 3, 4, 5.5 spaces above. So it should be 1, 2, 3, 4, 5.5 spaces below. So it should be about right there. So this curve looks like it's going to do this. And our horizontal asymptote should be x equals 4. 1, 2, 3. I'm a little bit off. I was off on that one a little bit. Hang on. At any rate, so our asymptote should be here. I think I counted that last one wrong a little. I think it should have ended up like, no, that was right. It was, where was it? There, and then the next one will be here, and then here, and then here, and then here. Okay, that's good. And then it will go that way. So that will be the curve. So then let's talk about, so our domain is still negative infinity to infinity. But our range now is negative infinity to 4. Our y-intercept is when x is 0, correct? So if we put 0 when x is 0, that's going to be negative 3, 1/2, negative 5, plus 4. So that's going to be negative 3. 2, 4, 8, 16, 32. That'll be 1/32 plus 4. Right? Am I doing that right? No, that'll be 32, not a 1/32. That'll be a 32. Yep, that'll be a 32. That'll be a 32. And then 32 times 3 is negative 96. That'll be negative 96 plus 4. So that'll be negative 92. So our y-intercept would be 0, negative 92, which matches up our picture pretty well. We are not going to have an x-intercept. It's not going to exist. But our limit, our end behavior is a little different. Our end behavior, the left-hand side, the limit of f of x as x moves to the left is going to be going towards negative infinity. And our limit of f of x as this graph moves to the right is going to be getting closer and closer to 4. And of course, you put that in Desmos or your graphing calculator and you can see that. All right. All we're going to look at here is this number, and we are asking ourselves this question. How far from 1? So this is 37% growth. Growth. I can almost spell. There we go. The pen's a little thick. This one is 1 minus 0.0 or 0.37. So it is 0.63. So it is 63% decay. This one is 1 minus 93. So that's 0.07. So it is 7% decay. And the last one is 258. 2.58 minus 1 is 1.58. So this is 158% growth. All right, my friends, that is it. If you have any questions, comments, ask in class, or send me an email.